I'm Niki Vazou. I'm a research assistant professor at IMDEA Software Institute. And today I'm going to be talking about Anosy, which is a joint work with Sanka, Marco, and James. And it was presented at PLDI 2020. So yes, Anosy stands for this approximated knowledge synthesis. And even though it has all these fancy words, and indeed it is about the knowledge that the attacker can get, it is implemented in Haskell. So in this talk, I'm going to focus more on this functional aspect of Anosy. So I guess you know that Haskell is this pure functional programming language, which means that it has very few effects, but it also has monads, which means that it lets the user design their own control effects. And this setup of being pure with monads is basically the ideal scenario to do information tracking. And this is because the monads can track exactly the information that they are using. And I'm going to explain that with an example. So here on the left, I have a monadic computation. It is IFC for information flow control. And on the right, I have a user, and the user has some sensitive data that IFC wants to access, but with control, right? So the dialog starts by IFC asking, what is your name? And the user is responding his name Bob, but this information is filled using this blue lock. So the IFC gets the name, but it is locked, so it cannot really go and access the name. Now, to access it, what it can do is it has to go and unlock this locked name. So IFC provides this function that is called unlocked, which takes as input a locked value, and it returns its value, so it opens the value up. But it has like also a lock state, which stores every lock that is opened, basically. So we have the locked name of the user Bob, and then IFC goes on and unlocks this locked name and stores the blue lock on the lock state, right? And so if I want to go and evaluate an IFC execution, I'm using this run IFC function that takes as input an IFC computation and some notion of permissions. And it says, if the accumulated locks that you used when you define the monadic IFC computation are below the permissions that you have, then run IFC is going to return the value of the monadic computation. Otherwise, it's going to throw a permission error, meaning that you don't have the permission to access the value that is derived from the IFC, right? And here I'm using this pseudocode, and my notation is a little bit free, because as I mentioned, like Haskell is the ideal place to do this information flow control. And there has been many systems that implement IFC. So for example, one of the first was LIO, labeled input-output, and it is using a lattice of dynamic labels, both to represent the logs and the permission, which means that all the policies and the labels can be modified at runtime. And then we have LWeb, that is LIO extended with web accessing. And also we have, like, recently we implemented Storm that is doing many of these information flow control checks. It is doing them statically using refinement types. And so what is impressive about all these applications is that they have been developed in Haskell and they have been used to do real-time systems. For example, LWeb has been used at University of Maryland to teach security and to implement many contexts. But all of them also come with very strong, like, formalized security guarantees that the implementation actually satisfies the permission checking that they promise. Okay, yes, IFC asked for the name of Bob, and he came back with a name, and it was unlocked using this blue lock. And then IFC can keep asking questions, and the user can come back with different permission statuses. So for example, now we are asking, who are your friends? and Bob comes back with the friends. I have friends X and Y, but it's locked in a yellow block, in a yellow lock now. And like you see, like the moment that I get the information, my lock state is not changing. But if I want to go and access the information, then I am adding another lock in my lock state. So now I need to run this execution, I need higher permissions or more advanced permissions. And then the last question that I am asking the user is to give me the exact location. And here I'm using the red lock because usually location is a very private information, and I need very high permissions to access the exact location of the user. So most probably, if I'm going to run this IFC that is accessing the exact permission of the user, I'm going to get a permission error, hopefully. So yes, because usually location is very well protected. But on the other hand, like we have all these location-based applications that we use every day. And for example, one of these applications is an application that can give you restaurant suggestions. So here Bob asked the IFC computation and says, do you know any good restaurants around here? And so what the application is going to do, it is going to basically derive a map of all the restaurants that exist around, and it's going to ask Bob, like, can you give me your exact location? And hopefully this is going to crash with a permission error. I cannot give you my exact location. This is very sensitive information. So what happens instead, what we can do instead is not to ask the exact location of Bob, but we can pick a restaurant that we would like to suggest, for example, the Green Burger, and we can ask, are you nearby this restaurant? And here in this, yes, and this are you nearby is implemented by a function that most of these IFC applications have, and it's called downgrade. So downgrade takes as input a locked value, a locked secret value S, and it is taking, it is not going to reveal the exact value, but instead it's taking a query on this value, like are you close to this location S, and it is returning the answer of the query, but without increasing the lock. So I'm downgrading the value, but I'm not going to reveal exactly the secret value, but I'm just going to answer a query around this. So the IFC here is using this downgrade to check if Bob is around this restaurant, and it asks, like, I don't need any permission to ask this. Bob responds yes, and now IFC knows that Bob is like in a close proximity to this green restaurant. And maybe you see where this is going, but if the IFC was an attacker, it could use this information that Bob is around this green place as a prior knowledge. And the key here is that it's going to ask, are you also nearby this red restaurant, this red burger? And if Bob says yes, then using the knowledge that I get from the second query with my prior knowledge, then I can know exactly where Bob is, and I have the exact location of the user without like actually requiring access, without having the privilege to access this information, right? Okay, so where we are, Haskell is very good at doing this information flow control, which is protecting users' private data, but all these realistic applications use this downgrade method that could be used from attackers to combine prior knowledge and to leak exact location or other protected data of the user. So in Anosy, we propose this bounded downgrade that is a variant of downgrade, but it answers queries on sensitive information only when we have guarantees that the posterior knowledge, that the knowledge, like the accumulated knowledge after we respond this downgraded query, is general enough. And by general enough, we mean that the user can set some policies. For example, a policy that we have here and throughout our example is that the size of the knowledge that you are revealing needs to be like greater than some value. So at least 100 values should belong to this knowledge that we're revealing. Okay, so this is how bounded downgrade is defined. Again, I'm being a little abstract for the sake of simplicity, but it takes as input a secret value s, which is locked. It takes a query on this value, and it is going to respond if the secret value satisfies the query or not. So it's going to return a Boolean value. And what is happening here is the first step is to unprotect my secret value. And this is a totally unsafe operation that like all the IFC system provide, and like unsafe IO. It's like, trust me, I know what I'm doing. I'm not going to leak this information, but I'm not like increasing the locks that I'm using. So unsafely, I am unprotected my secret value val. I get the prior information that I have in val, and the way that I get that is that now in our state, we also store a map that maps secret values to A, which is a knowledge, like a prior knowledge that I have over these secret values S. So I'm getting the prior from my state, and then I have a magic function here, posterior, that based on my prior, my secret value and the query, I compute the posterior knowledge that I have. And then if the posterior knowledge satisfies this general enough policy, for example, that the posterior has size greater than 100, then I update my prior to the current posterior, and I return the result of the query on my secret value. Otherwise, I throw an error, right? Okay, so there are two things to observe using this code. The first one is, like, as I mentioned, I haven't yet defined how to compute the posterior, so we're going to do that next. But the other interesting thing to note is that this bounded downgrade doesn't have a real dependency over the IFC. So I'm not using its state. So the only thing I'm really using is this unprotect that most IFC libraries define, a way to like unsafely escape all the protection mechanisms. But this observation is interesting because since like this bounded downgrade is not bound to like a concrete IFC implementation, then we are going to use a Monarch transformer to define it. So the only interesting thing that I'm changing here is this wrapper of the secret values that I say, okay, it's some lockable thing L that the IFC that I'm going to transform should define somehow. And also I am defining the state of the Anosy, a monad that like essentially keeps track of the policies that I'm enforcing and also maps each secret to the prior knowledge that I have revealed. Okay, so we defined downgrade as a function on the Anosy monad transformer that keeps track of all the information that I'm revealing. And again, like I think this is like a very cool upgrade from being very tight to one specific monad, because as I mentioned before, Haskell is the ideal place to do IFC, and there are all these very nice libraries that do it. And like the claim here is that you can use bounded downgrade on top of any of these IFC libraries. Okay, so essentially we keep track, for each secret information, we keep track of the revealed information. And now we go to the difficult part, which is how do we compute this posterior knowledge, right? So we have a query on some secret values. We have a concrete secret, and I have a prior knowledge that I'm calling A, and this type class tells me that A is a knowledge over S, and like given these arguments, I just want to compute the posterior. So what is knowledge? In Anosy, like basically a knowledge is a set of secret values, and in Anosy we define it using this type class. So we have like two constant knowledges. We have the top, which is the full set. We have the bottom, which is the empty set. And the interesting operation that combines both the secret and knowledge is this belongs, because I need, like, I really need to know if a secret belongs into a knowledge or not. And then we have two set operations like subset and yes, conjunction, no, intersection. Okay, subset and intersection. And okay, so we define knowledge to be a set of secrets. And so the challenging part here is that if you have like any abstract, like any random knowledge, precise computation of knowledge operations can be uncomputable. So, for example, maybe my knowledge is infinite. So, taking if a concrete secret belongs to a knowledge can take forever. Or the other like very common part is that knowledge takes very concrete, very weird like shapes, depending on the queries that you're using. So doing intersection of weird shapes leads to more weird shapes, and then like computation becomes very, very, very slow. And as it's like common when you're dealing with knowledge, what we're going to do is we're going to use abstract domains to basically approximate the knowledge that is revealed after each query. So let me explain this again with an example. So we have the basically nearby, are you close by to this restaurant, running example that IFC asked Bob. And here we are becoming more concrete. So to define location, I'm using a Haskell data type that has the X and Y coordinates. My map is like a finite map here, and I define a nearby function that is basically computing the Euclidean distance of two locations. So here I'm setting my secret to be a location, the user location, and I have a very concrete query that is asking, are you nearby the center, like 200, 200, right? And the knowledge, the precise knowledge that I am getting after asking this query has this shape. So basically this query splits my map into two areas. The yes area, that is the light one, which says that, like, yes, the user is nearby my center, and the dark area that is known. So, like, if the user asks yes in this concrete query, then the attacker can infer that the user is somewhere in the light area. And like contrapposite, if he answers no, like the attacker can infer that it's somewhere in the darker area, right? So as we said before, representing a precise knowledge easily, like quickly becomes very, very difficult. So what we are going to do is we are going to approximate the knowledge. And in this case, we approximate using intervals. So I'm approximating an integer using this knowledge of integer data type that is between low and high. So I am using one interval between low and high to approximate some integer in my space. And then to approximate data that contain integers, basically I'm using one k-int for each integer. So to approximate location that has two integers, x and y, I'm using the knowledge of x integer approximation and the knowledge of y integer approximation. And then we have, and it's like quite straightforward to see how we can define an instance that says that the k approximates my secret, where my secret is the location, right? And so yes, this was my concrete knowledge, and I'm going to approximate it with the intervals. So this is one interval approximation. And the interesting part, like the correct part, is that the yes area, that is the light area, belongs inside the rectangle, and the no area, again, it's like a rectangle that belongs in the no of the real knowledge. And this is like how this shape is defined in Haskell. So my approximation has two intervals, the yes and the no. And the yes is defined like as this shape that, like, if you do the calculations, you can see that it is actually the shape. And the no area is easier because it starts from 0, so it goes from 0 to 400, from 0 until the end, and then from 0 to 99. So like it is easier to check that the no area is correct, and the yes, like, I guess, like, I don't know how good you are in math, but we could assume that this yes area actually belongs to this rectangle. So the good thing, like we define an approximation of the knowledge after I ask it a query, are you close to the center? And the good thing is that having this like simple approximation, our goal is easy. And our goal was to define this posterior function that given a secret and the prior knowledge, it computes the posterior knowledge after I ask the query. And having this easy approximation of the query knowledge, this definition becomes quite straightforward. It is the prior knowledge intersected with if my query is true, then I take the yes approximation, otherwise I take the no approximation. So that's the easy part. But I guess, like, I don't know if you agree, but the unreasonable part is that the user has to compute all these like integers. So yes, the question here is how do you come up with this approximation? And even if you like manage to do the math and you figure out the approximation, how do you know it is correct? I mean, in this case, we are in the 2D, two dimension, and we saw the picture, so maybe you are persuaded that's correct, but in the general case, I have more dimensions, and like coming up and even checking that these are correct is not so straightforward, right? And yes, from the title, and we're going to use refinement types to solve both this question, both these problems. And concretely, we are using Liquid Haskell that has, it's a refinement type checker for Haskell, and it has this nice feature that is called abstract refinements. And basically, abstract refinements let you take a data type and embed some properties. Like here, I have the property P, and basically they give you the flexibility to define what is the meaning of this property. So we did some engineering that the details are in the paper, or like we can discuss later, but we define this K such that P to describe all the elements, all the knowledge whose elements inside this knowledge satisfy the property key. And the asterisk here says that, like, remember, a knowledge is a set of secrets. So everything that belongs in the K, all the secrets that belong in K should satisfy the predicate P. So having this nice abstraction, it is quite easy to say that to declare the properties that the yes knowledge and the no knowledge have. And for the yes knowledge, we say that it is a knowledge, and all the elements that belong to the knowledge actually satisfy the query. And for the no knowledge, we say the opposite, right? All the elements that belong to the knowledge don't satisfy the query. And so all the elements that belong in the yes area return yes on my query, and all the elements that belong in the no return no to the query. So we give this specification with abstract refinement P, and then Liquid Haskell can actually go and verify that the yes knowledge and the no knowledge are indeed like this under approximation of the query knowledge. But yeah, still the question remains, how do you come up with all these indexes? And like the interesting observation is that refinement types can also help you synthesize such knowledges. So refinement types have this nice property of like localizing the logical information that you have. And in the past, they have again been used for synthesis because of this locality that they give you. So here too, like what we did is we gave the refinement type, the proper refinement type to the yes and no knowledges, and we implemented an algorithm that is synthesizing all these indexes for you. And what is happening exactly is the first step is we use like the syntax-directed synthesis and Haskell's like basic types to generate the form of the knowledges that we want. So here, like, we just leave all these integers as variables or as wholes, as they say in the synthesis word. And then in the second step, we use the refinement type decomposition to generate the constraints that we want to get satisfied by these unknown up to known variables. So we say that for its x and y locations of the user, if x is between the low and the high, and y is between the low and the high, then the location of x and y should satisfy the query. And we get this property by this refinement type. And also, like, it was very important to generate this also maximization request and say that we want to have like the biggest possible distance between the low and the high, because otherwise, like, our synthesis algorithm is iterative, so it will always come back with empty domains. But yes, we generate these constraints and we give them to an SMT solver. We use Z3 because it has a nice maximization construct. We give them to Z3. It comes back with concrete indices, and then we just like plug in the holes and we generate this abstract domain for the yes knowledge, and the same for the no knowledge. So, where are we? So, Anosy defines this bounded downgrade function, and the Anosy monotransformer basically keeps track of the prior knowledge that is leaked every time we downgrade a query on a secret. And again, the challenge there was how do you compute the posterior? And to compute the posterior, we use this combination of knowledge abstraction and synthesis, which means that for every query that the user defines like syntactically at compile time, Anosy is going to generate an abstract knowledge. And to do that, it is like this abstract knowledge is synthesized using SMT solver. And also, like after synthesis, it's verified via liquid Haskell that it indeed provides, like in this case, a under approximation of the real knowledge. So all this is implemented in Haskell, and AnosyT defines this monotransformer, and we have like many the knowledge type class and some instances that we have implemented and verified. And also, like, there is a lot of pre-processing that is happening to synthesize the knowledge, and this pre-processing is happening as a GHE plugin where the user defines like all the queries and we go and analyze all the queries. So you cannot do a downgrade to any arbitrary function. Yes, and concretely, like the queries are straight-line Boolean functions, by which I mean we cannot have recursion because the idea is that all the queries you define are encoded into Z3, like by direct encoding Haskell to Z3. And the secrets that we have used are basically products of integers because we have only abstracted integer in these examples that we used. And for abstract domains, we did the intervals that I presented you the example before. And we also have like power sets of intervals. And by this, like here, I am abstracting the knowledge of the are you close to the center query using intervals. And here I'm using power sets, by which I mean like that I have many intervals at its case. And for the no, I have 4 intervals. And for the inner, I have 3 intervals. And like, as we will see, yes, we will see it now. So yes, this is our evaluation. And so we use these 5 case studies as the first evaluation. And we took all these case studies by a probe work that is also doing approximation of knowledge, but it is doing it dynamically and using different methodologies. But we took these 5 case studies that they apply at our settings, and we have here like 4 dimensions. We have under approximations, which is what I presented, so the approximated knowledge is always smaller than the real knowledge, and we also have this over approximation, and we have like 2 abstract domains here. We have the interval that I showed, and also we have power sets of intervals of size 3. So like its knowledge has basically 3 rectangles in the 2D space. And what do we see? Like the synthesis time is quite reasonable. It is like a probe, for example, that it's doing dynamically, it is faster. But the good thing with Anosy is that all the synthesis and all the pre-processing is happened once at compile time. So it makes sense that we are like slower than runtime synthesis tools. But it is quite reasonable. And of course, like the simplest the abstraction domain is, the faster it goes. So here we have 1 second, and with intervals, with the power sets, we have about 30 seconds. And the other interesting thing to note here is accuracy of our approximation. So here we have the real size, and here we have the size of the domains that we inferred. So lower is better. So for example, here the size of the domain is 259. Here we also have 259, so the difference is 0. Lower is better, but here, like in this example, we went quite off. And yes, like comparing these results, you can see that the more precise the approximation, so when we have power sets of 3, the better the precision we have. And we also did another interesting case study. So this is again our location example. So what we did is we have a user and we keep asking him if they are close to some like location that is randomly generated, and we evaluate when it is going to generate a policy violation error. And the evaluation here, like K, is the size of the power sets that we used. And for example, with one power set, we have intervals. So we asked 8 queries until it says, I cannot keep answering your question. But when we increase the number of the power sets, the number of the intervals we use to approximate, we can ask the user more questions. So basically, the more refined the abstract domain that we have, the further we can go asking the user question without losing a lot of information. So, okay, so in summary, as I mentioned at the beginning, and I think I like maybe I said it too much, Haskell is the ideal setup to do this information flow control because like it is designed to explicitly track information that goes into the monad and gets unlocked, and we have all these amazing tools that are implemented to do IFC in Haskell. And they come with very strong security guarantees, but all of these guarantees break the moment that realistically the application needs to downgrade this information. And downgrading the information can potentially leak private user information. So in Anosy, we implemented this bounded downgrade that has 2 key features. One is that we have this Anosy monotransformer that keeps track of the prior leak knowledge that the user, the attacker can have. And then for each query that we are downgraded, we synthesize using SMT the abstract knowledge that is leaked, and we also verify this synthesized knowledge using liquid Haskell. And again, this is presented in PLDI this year. Here is the information of the paper that comes with the artifact. So all the code can be found here. And I am Niki Vazou. I am assistant professor at IMDEA Software Institute. And since I have the stage, I can say that I am always looking for PhD students and interns. So let me know if you are interested. And with this, I would like to thank you for your attention.
I hope you could hear the round of applause.
Yes.
So folks, do we have any online questions? No? Any questions in person?
Hello, very interesting talk. I was wondering exactly what makes Haskell ideal for this setting. Couldn't we, for example, in an impure language, have a thanks computation that we, for example, track the information in some mutable state and abort with an exception when we know too much or something? Why is exactly Haskell so good?
I think Haskell gives you for free what you described, no? So there are information flow control mechanisms for non-pure language, and there what is happening is when you have like a secret value, you wrap it again in the lock, but you don't have this nice unlock operation that automatically keeps track of the state. So then like you want to define computations for like locked values. So for example, if you have 2 locked integers and you want to add them, you cannot unlock them because maybe you forgot to keep track of it manually. So if you want to add 2 locked operations, you need to define a different function that is lifted, as we would say in Haskell, and like unlocks them and then like computes the least upper bound of the two locks and then generate another locked value. But in Haskell, like once you unlocked it, you do it once, and you haven't like you ensure a mechanism to keep track of the locks for you. So it can happen in other ways, but in Haskell it's more natural and like you get all the guarantees for free.
All right. Any more in-person questions?
Yeah, so I was wondering if you could speak a little bit about if there are any limitations to the domains. So you only had like the interval and powerset domains, but are there other interesting domains, or is there some reason why you didn't implement others?
Yes, I mean it's complicated. Even for the powersets, it was not easy because so the type class that we have is verified because like I simplified things quite a lot, but to verify like we used liquid Haskell to verify the synthesized things, and the synthesized thing use all these intersection and set operations. So for each abstract domain that you define, you need to do two things. One is you need to verify that the type, the class instance satisfies the properties that you want to satisfy. And the second is you need to define how you synthesize such abstract domains. And like I remember we tried one more, maybe the octagon abstract domain, but the synthesis it didn't work because by default, like Z3, when you ask it to synthesize stuff, it is enumerating. So it starts from 0 and it goes up. And you need to be sure that this maximization principle is simple enough and it works. So yeah, the short answer is we tried one more abstract domain, but like it was not obvious.
Okay, so any more in-person questions?
Hi, thank you for your talk. I just wanted to ask whether you also take into the consideration that the fact that you like cut the discussion with any other party after like reaching the threshold of the posterior information. So the fact that you cut the discussion also modifies the posterior. So my question is whether do you take that into consideration? Because if not, there could be specialized attacks that could revolve around that.
You mean that by answering no, by telling you that I don't have the privilege, you can get more information?
Because you stopped answering, you gave more information, basically.
So the attacker can infer like that since I answer it, maybe it is yes, maybe it's not. I mean we don't have a formal proof that the policy is not violated, but I was quite persuaded because I think the actual implementation computes the posterior and then it decides if I'm going to throw an error or not, and the posterior depends on the secret. I cannot. I'm thinking. I mean, what you say makes sense. That's telling you that you violated my policy leaks information, but yeah, I guess I don't have a good answer because I was persuaded. Like when we were writing the paper, I was persuaded that this is not the case anymore. But the persuasion argument obviously was not clean enough so that I can reproduce it.
Okay, thank you.
Okay, I think we have time for one more question. And I think that's it. Thank you, Niki.
Thank you very much.
A round of applause, folks.